Hello, everyone. Thanks for the opportunity to present our research work in the fifth National Conference on Innovative Computing IC 2022. I am Khalil Rehman, PhD candidate at Beijing University of Technology. Our research topic is a feature fusion-based approach for mammographic mass classification using deep learning. The content of this presentation is as introduction, literature review, research method, experimental analysis of results, and the conclusion. Introduction. Breast cancer is the leading cause of morbidity and death among females in all specific disorders. According to the recent study conducted by the International Agency for Research on Cancer, prevalence of breast cancer is rapidly growing around the globe, with over 2.3 million women diagnosed each year. Due to its excellent diagnostic sensitivity for any lesions, mammography is commonly utilized in early breast cancer screening. So breast mass identification and interpretation using digital mammography is a time-consuming job for radiologists. In breast cancer diagnosis, computer-aided diagnosis systems and technologies are used to elevate radiologists' load of digital mammography pictures and increase their diagnostic efficiency. Among the different types of breast abnormalities such as masses, microcalcification, architectural deformities, and asymmetries, the breast masses are complicated to identify from comparable background because of their changing size and poor contrast impacting diagnostic outcomes on mammograms. Literature review. The texture analysis in mammogram images can be used to glean complicated visual patterns. Suspected areas may be analyzed using this method by examining textual characteristics. There are many studies utilizing texture features or texture analysis for the detection of masses from digital mammograms. There are several limitations in these studies. For example, Occitan employed gray-level co-occurrence matrices for texture identification and classification. The author D. Ruth et al. Used combination of diversity indices and GLCM gray-level co-occurrence matrix to detect the texture of breast tissues and obtain 88.31% accuracy. Professor Abbas et al. Extracted texture features from DDSM datasets using GLCM and achieved 91% accuracy. Current issue in current mammography mass classification with CNN is the absence of locally invariant features that cannot effectively adopt to dramatic imaging angles. For this problem, the texture MR filter bank is capable of capturing subtle changes in the texture of the pictures and accurately modeling the breast mass identification. Previous study shows that the detection of breast masses using the texture analysis from digital mammograms was challenging due to its varying patterns. So these methods successfully implemented the texture analysis from digital mammograms and achieved lower classification accuracy. So to counter these problems, in this study, we investigated the limitations of texture analysis for mass detection by creating an MR filter bank, MR taxon filter bank using Laplacian of Gaussian. We created a deep taxon feature fusion bank for the proposed efficient deep neural network to classifying malignant and benign masses. The proposed framework pertained to the steps such as image preprocessing and augmentation, feature fusion and taxon filter bank creation using the Laplacian of Gaussian, and the classification of deep feature fusion bank with efficient deep neural network. The complete proposed framework is presented in figure 1. As we can see that we acquired the mammogram images, and then the two steps implemented. First, the DICOM images is converted into PNG format, and then the dataset should be increased artificially using the data augmentation techniques. Deep CNN features. After that, we have label and segmentize the mammogram images using image-wise labeling and detecting the masses from the mammogram images using the Laplacian of Gaussian and creating the feature filter bank. After that, the filter bank and the feature fusion features classified using deep convolutional neural network based features. So in this study, we have proposed a efficient net-based deep convolutional network for the classification and also compared with very well-known other deep learning networks such as MobileNet, AlexNet, and TenseNet. Our proposed method classifies masses into two classes, the malignant and the benign. For evaluating our proposed model, two data sets, the local pinum and the private public data set. The local pinum data set is conducted from the Pakistan Institute of Nuclear Medicine and Radiology, and the other public database CBIS DDSM. The Genome dataset includes 577 original images, including 425 benign and 152 malignant images. The CBIS curated breast imaging screening, a digital database screening mammography, is a publicly available dataset which contains 10,239 images, from which we included the 4,000 digital mammogram images, which contains 2,250 benign and 1,750 malignant images. In the first steps, we are applying the image preprocessing, the computer vision algorithm for the conversion of DICOM images into PNG format and resized using the zoom in and zoom out functions, and the polynomial interpolation functions was implemented to generate the new data points for resized images using the original pixels. The images are rotated using the data augmentation techniques at the angles of 45 degree, 65 degree, 145 degree, and 175 degree. The dataset size of Pnum increased up to 3,462 images to train the deep neural network. So Laplacian of Gaussian filter. A filter set based sector feature extraction method is employed to create in-depth CNN features for masks that describe the different pixel associations in a particular region of an image. We create an MR filter bank for an acceptable response to the directional texture using isotropic and anisotropic filters. MR filter bank consists of 8 filter banks. The two filters, Gaussian and Laplacian of Gaussian, are implemented for creating an isotropic filter bank. So let G be defined as an Gaussian filters first and second derivatives for the kernel function and can be calculated using the equation 1 and the equation Laplacian of Gaussian equation 2. After creating the feature taxon MR filter bank, the fusion features of deep CNN was created. In image recognition, feature fusion techniques are often employed to accomplish feature complementation and overcome a single feature vector. Two fusion methods are proposed to find the best way to use the complementary information, including interpretive. The direct fusion is implemented for creating feature vectors using the function of defined in the question 3 d of f is equal to d of fb in x and n, where xcnn is a deep CNN features vector and dfb is a more filter bank. The dimension of CNN features is 3 times the feature vectors. After creating this diffusion feature CNN features, we feed these features into our deep convolutional neural network. So the proposed neural network is efficient convolutional neural network design and scaling technique that uses compound coefficient to equally scale all depth, width, and resolution parameters. We develop an architecture consisting of one input convolution having 3 by 3 6 mobile inverted bottleneck MBC convolution, 3 by 3 kernel, and 9 mobile inverted bottleneck convolution sets with the 5 by 5 kernel, the pooling layer, and the two fully connected flattened layers. The kernel size 3 by 3 was used to create an input feature map with the RELU activation function using the deep CNN fusion features. The output layer uses the softmax classifier for the classification of benign and malignant masses. The figure 1 presented the complete architecture of our deep neural network. So this is that neural network architecture. The input images, the pooling layers, the convolution layers, then the pooling layers, and then the convolution layers, and then the at the end fully connected flattened layers and the softmax classifier for the classification of malignant and benign masses. So experimental results evaluated on local PNM and the CBIS DDSM datasets using the four pre-trained models, the proposed EfficientNet, MobileNet, AlexNet, and the DenseNet. Dataset was separated into training, testing, and validation with the ratio of 60-20-20 using five-fold cross-validation. Figure 2 and 3 reveal that training loss consistently decreasing and accuracy increasing on both datasets uh, as compared to other networks. Our proposed network performs much better, which means the model is well fitted. The performance of the proposed method was 11%, 4%, 6%, and 10%, 7%, 12% higher than the MobileNet, AlexNet, and DenseNet on the Plenum BDISM dataset. In terms of accuracy, figure 4 and 5 present the accuracies. So here is the training loss and accuracy of our proposed method. On both datasets, we can see that our method achieved maximum accuracy and lower training loss as compared to other networks, which means the performance of our proposed method is much better than the other one. So this is the accuracy comparison. On the PNM dataset, our proposed method achieves 0.96, while on the DDSM, CBIS DDSM dataset, we can achieve 0.98 accuracy, which is higher than the other networks. So figure 6 and 7 reveal that the specificity for evaluation of our model, we also diagnosed and evaluated specificity and also the area under the curve for our proposed method. Specificity was 9%, 11%, 8%, and 12%, 25%, and 21% higher than the other deep neural networks on PNM and CBA's datasets. Similarly, the area under the curve of our proposed model was also better than other deep neural networks on PNM and CBA's datasets as shown in figure 8 and 9. The above results indicate that the classification of masses with the proposed deep neural network is much better than the other deep neural networks. Similarly, we compare it with the previous studies. Table 1 presents that the proposed method achieved the higher accuracy on private and CBIS DDSM datasets than the previous studies. This is the specificity comparison with the other neural networks. As we can see that 0.87 we can achieve on the PNM dataset and 0.95 on the CBIS DDSM datasets. So here are the area under the curve. If we can see that on premium data set we can achieve 0.80, while on the TBS data set we can achieve 0.85, which is higher than the other networks. So here is the experimental result analysis with the previous studies. If we can see that the maximum accuracy was achieved by the Author 13 0.97 on DDSM dataset, while on the CBIS DDSM dataset was 0.93. While our proposed method achieved using the taxon feature fusion based method, CBAS dataset DCSM, DDSM 0.98 and 0.96 on private dataset, which is higher than the previous approaches. So texture analysis is defined by the complicated visual patterns of mammogram images. Therefore, the automated computer-aided diagnostic system was developed to detect and classification of breast masses. So here we concluded that this study proposed a novel automated computer-aided diagnostic system to detect breast masses from digital mammograms and perform classification using feature fusion-based deep convolutional neural network. So from the previous experimental results, we can see that experimental results demonstrated that the proposed method achieves higher results than the other neural networks and the previous studies. So the image texture fusion based method is much better than the other previous approaches, which increase the pixel intensity, and for this we can achieve the maximum accuracy. Our proposed method achieves the highest accuracy rate as compared with the previous study, which shows that this method should be helpful in real clinical daily routines. Thank you very much for this opportunity. Have a nice day.